Hi guys, so my name is Edgar and today I'm presenting on memory cache mapping techniques. So it's memory cache mapping techniques. Fundamental strategies used in computer architecture to determine how data from main memory is stored and accessed in fast cache memories. So the interaction between the cache mapping techniques and virtual memory systems forms the backbone of the modern computer memory hierarchies. So understanding these types of systems working together is essential for optimizing performance and managing the complex flow of data from virtual address space through physical memory to cache storage. So I'll go ahead and talk about the memory hierarchy. So with the memory hierarchy, modern computing systems employ multi-layered memory hierarchy where virtual memory provides the programming abstraction, physical memory serves as the primary storage medium, and cache memory offers high-speed data access. So each layer uses different addressing schemes and management techniques that must be carefully coordinated. So the way there is coordinated, they must be carefully coordinated. Then move on to talk about the memory hierarchy layers. So with the memory hierarchy layers, we have the virtual memory space, which is the programmer's view, the physical memory, which is the actual RAM, the cache memory, which is the high-speed buffer, then processor registers, which is the fast access. So when you watch the slides, you can see there's a diagram there showing the memory hierarchy layers. So the memory management, which is also known as the MMU, handles virtual to physical address translation, while the cache controllers manage the movements of data between physical memory and cache storage using memory mapping techniques. So we move on to talk about the virtual memory. So the virtual memory creates an abstraction that allows each process to operate as if it has to access a large contiguous address space regardless of the actual physical memory configuration. So the key components are the page tables, translation look aside buffer, which is a TLB, then page fault handler, which manages access to swap out pages. Then memory management unit, which is the MMU, it performs address translation hardware. Then we want to talk about the benefits of the virtual memory. So with the benefits of the virtual memory, it enables memory protection and process isolation, allows programs larger than physical memory through paging. It facilitates memory sharing between processes, provides consistent memory layouts regardless of the physical constraints. So we want to talk about the system with virtual memory. So the virtual memory has a system, and when you watch the slide, you see there's a diagram there showing how the virtual memory is like a system of the virtual memory system with that. So I would like you to go through that and see very well what it entails. So the cache addressing schemes. So the cache addressing scheme, the relationship between the memory and the cache system depends critically on whether cache operates using virtual or physical addresses. So virtually addressed cache, which is known as a VIVT, then physically addressed caches, then hybrid address. So with the virtually addressed caches, the advantages are one, the fastest possible cache access since no translation is required. And the disadvantages, the context switching overhead. Cache contains may need invalidation when switching processes. It's very true, that's very true. So we move on to talk about physical address cache, the advantages and disadvantages. So with the advantages, eliminate identity problems completely. Then with the disadvantage, increase access latency due to the required address translation here. Then the hybrid addressing. So the hybrid addressing virtually indexed physically tagged caches. So this approach uses virtual address bits for cache indexing while using physical address bits for cache tagging. So implementation strategy. So virtual address bit selects the cache set to brackets, which is the index. So the physical address bit after translation verify the cache hit to brackets tag. And the MMU translation and cache indexing occur in parallel. So So talk about the direct mapping with virtual memory. So with the direct mapping with virtual memory, each memory block maps to exactly one cache line. With virtual memory, this relation becomes more complex due to address translation. So virtual memory impact. The mapping formula becomes cache line to bracket which is the physical address after translation, the number of cache lines. Then we go on to talk about the set associative mapping with virtual memory. So the set associative cache divided the cache into sets. Sorry, with each of the containing multiple ways. This approach balances the benefits of the direct and fully associative mapping, accommodating virtual memory systems. So virtual memory integration, cache sets can be aligned with virtual memory page boundaries. Then the page coloring becomes more effective with multiple ways per set, reduce sensitivity to virtual address allocation patterns. And then we will talk about multiple level cache integration. So with the multiple level cache integration, different cache levels may use different mapping strategies, optimize their specific role in memory hierarchy. As you said earlier, we've talked about memory hierarchy already here. So typical configuration, which is the L1 cache, it's fast access with so the L1 cache, fast access with simple mapping, then L2 cache, larger capacity with moderate associative, then L3 cache, maximum capacity with high associative with complex mapping. Then we talk about performance optimization strategies. So address translation optimization, which is TLB, design large, perfection, then other styles here. Then we talk about modern implementation considerations. So with the modern implementation consideration, the those set associative mapping to bracket the 4 to 8 way common, the VIPT addressing for L1 caches, the PIPT addressing for higher level caches, then integrated MMU and cache controller designs. Then in conclusion to what I said, cache mapping techniques to bracket direct associative and set associative determine how virtual memory addresses translate from physical memory to cache storage. With set associative, VIPT caches provide optimal performance, competitive balance. So when you watch the diagram there with the slide, it shows how like everything about the cache memory, how it operates and stuff. So I would like you to go read on the slides again and check the diagrams very well to see what I'm talking about, and I'll see you in my next slide.